All right, thank you, Olaf. Thanks for introducing the talk. I think I'll just get right into it. I should maybe say, let's get real, because now we're talking about like real stuff. No shade. So I'm going to talk a bit about these systems that I work on. These are like self-propelled systems far from equilibrium, and they all depend, or their motion depends on the Marangoni effect. So in this case, you have a particle or a droplet that's deposits surfactants onto a water surface, and these surfactants will lower the surface tension of the water, which then will create like a gradient in surface tension, because some of these molecules also get removed at the same time. So in the case of, for example, camphor, it evaporates from the surface. So this is basically so that creates a sort of convection in the bulk of the water that then again leads to like a surface flow. And of course, in the case of a camphor particle, let's say if this was a perfect system, right? Let's say the particle would be perfectly round, it would be perfectly in the middle, and there would be no airflow. Technically, it shouldn't move at all, but like these small perturbations that are introduced into the system, they lead to this kind of chaotic behavior. And in this case, I want to talk about a special system that was actually first introduced by Shinpei Tanaka from Hiroshima University. And this is a collective of ethyl salicylate droplets. In this case, they're like ethyl salicylate mixed with some paraffin to make them float on top of an aqueous solution. And the solution already contains a surfactant. So there's already a surfactant at the surface. And these droplets will, at least that's what we think, we're not 100% sure, it will so the ethyl salicylate will be deposited onto the surface, and it will locally lower the surface tension even more. But then what happens is that the ethyl salicylate goes into solution together with some of the surfactant that was already in the solution, which will locally again actually raise the surface tension, because you remove both surfactants in that case. And that, of course, leads to the fact that the system will mature in a way, because it's closed, we cover it with a dish. That means both the bulk and also the atmosphere will slowly get saturated with this ethyl salicylate. And that will slow down their movement. And so that's why we get this kind of balance between the repulsion between the particles, their motility, and the capillary attraction between them. And if you have the right initial conditions, then you get quite interesting behavior, such as this periodic ring formation. That's what Shinpei discovered. So this only happens when you have the droplets so this is a dish that's around 9 centimeters across. The droplets are a couple of millimeters big. And so they will go through this periodic behavior. And this is, of course, just one stage in their whole evolution. So usually these experiments take like 20 hours, and we just film them, and as you can see, it's sped up quite a lot. So this was the origin of this. So of course, Shinpei already did this, and I thought, okay, what can I do? I started to play around with some with the parameters of the system, and one of them I discovered was that actually the dye that we sometimes add to these droplets actually affects the behavior significantly. And this is just to showcase that. So you can see, for example, it still goes through the same evolution, but at slightly different, let's say, time intervals. And if you start mixing the two, then you get, again, then you can actually see the different behavior. So on this side, you can see it. The red droplets are more active than the blue droplets, and they actually end up kind of encapsulating, or like they tend to be more on the outside of the system. So that's quite interesting to us. But that's actually something I talked about in the past at the workshop, so I'm not going to talk about that. So then you have to go check the video. What I'm interested in for this talk is actually the population density. So there's another major parameter we can change that actually affects behavior quite drastically. So if I open this video here. So in this case, when you have, maybe we just stay here, and I speed this up a little bit. So here you have many more droplets. So they don't have space to make like one large ring. So they end up making these kind of honeycomb structures, for example. And In this case, it acts a little bit different because again, it's a different dye. So how the system like rearranges is when two droplets fuse, and then oftentimes they just fall to the bottom of the dish. So that's what you can see there in the lower left corner. So that's why they look different. You can see here something happened again. And yeah, so this is, okay, so this is when you have a high density. What I really find interesting is when you have a low density. So let's see, we open this video here. So again, at the beginning, the system behaves quite, they all move randomly. Let's speed this up a little bit. But if you get, I'll just sit down for a second. If you get to a certain point in the system, they start to form these clusters. And in this case, because they have a lot of space, they form smaller clusters. And what we see is that every time we repeat this experiment, they will form the same type of cluster. So there's some sort of, in all of these, I guess, a sort of emergent behavior from the mass of them. And for example, these guys are quite interesting. I call them like the third wheel. So there's two, like a dimer of droplets and one that's just like hovering near to them. So there must be some structured convection at this point. So they're quite interesting. But if you move on further, then you get to a point where you also get, let me just move this ahead here a little bit. Oh, this is too far. So at this point, you get some clusters that are actually like translating across the dish. And so this is like at a later stage. And just to show here, I just collected some of these clusters that we tend to see again and again. So in general, we get like a longer and longer chain formation. And eventually, maybe I should show that quickly. What happens at the end of the system is, this is like the death state, is that they just basically crystallize, or they basically make these hexagonal patterns. Technically, you can revive them a little bit by lifting the dish, because then you renew the atmosphere, so then they will spread again. But it turns out that the droplets do somehow age, so we cannot really revert them back to, or at least not yet. I'm trying to figure that out, but that's maybe for another time. But so I found this really interesting, this behavior. So that's why we started to go from phenomenology to actually want to kind of start quantifying these systems, which is quite difficult because you need to keep identity of the different droplets, but also maybe we want to track cluster sizes over the time of the whole, over the whole evolution of the experiment. And this is like the preliminary work we have, or that actually Shinpei and his student have done thus far. And it's it can do it a little bit, but for example here, it's difficult to decide when is what a cluster, and so we need to train the system, I guess, or the script to be better at detecting the clusters we are interested in. But what we can do so far with this is that we can at least make some graphs, which is nice because it's difficult to put a 20-hour video into a paper. So here we can, for example, we can at least see that smaller clusters tend to live in the beginning of the experiment. These medium clusters, they have their own little, let's say, timeline. And as the system ages, these really large clusters tend to prevail. And of course, in the end, we have actually just one huge cluster. And here's just, we try, it's a bit difficult to show that, but for example, like you can see that you can kind of see the dynamics in the system from the monomer speeds, because we do sometimes have monomers or like single droplets later on that they really slow down. But in the slow part, that's where we get the more interesting behavior. And of course, this is maybe a bit chaotic, but at least it shows that in the same kind of velocity range. And we also try to kind of make an overview of which clusters are existing when, like similar to the picture before. So we're experimenting a bit with different ways to show that, but that's definitely still a work in progress. Just wanted to show where we're at, and yeah, that is difficult, and they're always happy to hear suggestions about that stuff. And this is the most recent that Shinpei's student did. They did these hierarchical clustering analysis, which like short as HCA, and Sten Rasmussen always calls them Hans Christian Andersen diagrams, because he's from Denmark. But this is just another way to kind of follow the kind of clustering behavior over time. So you can see there's some different time steps here. And as time progresses, we get For example, here would be droplet number 7 is in a cluster or is close to 21, and they form a cluster with like maybe 2 others. I don't really understand these very well yet, but maybe next year I can explain them better. But at least they show, again, we have this, maybe we can use them to quantify the clustering behavior. And now I actually come to maybe why this is like playful in a way. I mean, it's fun to look at, it's fun to play with these systems, at least in the lab. I enjoy that immensely. But what we see is that these, especially these clusters that tend to move across the dish. So first of all, they're quite important in like mixing the system, because they move across the dish from, let's say, one cluster to another, then they scramble and shoot out another one. So they kind of distribute themselves. So it's almost like a sort of droplet society of sorts. We found that interesting, and we want to explore it further. This is, of course, all quite preliminary, but what we also try to include in this work is, because every time I show this to someone in this community, they say like, well, that kind of looks like a glider in like a game of life. So there's a similar behavior here, especially when they, you know, because they move, they collide, they destroy themselves and reform themselves. So you almost have like gliders, you have like glider guns, which we find quite interesting. Just to show what that could be like. So in a way, you have the same experience here as people have with the game of life, right? When they look at it and they discover these patterns by just looking at it. So you can do the same here, and then you can go back and change some parameters and get a different outcome. And I don't really know what the implications of that are, but again, here I just showed for the people who are not familiar with the game of life. It's just something I found on YouTube, so a sort of example of some gliders, and that they do different interesting things, and you see like similar behavior. And of course, so what's important in this case are the rules, right? So what if I can figure out the rules of my system? And of course, I would have to do that through doing many experiments, getting out all the data, and maybe we can get, let's say, the macroscopic rules, because the microscopic rules are extremely, you know, complicated. And if you want to solve this like analytically, it's very expensive. So yeah, I mean, admittedly, it's the comparison with game of life or other cell automata is just reminiscent. Like it just looks like it. So far we haven't done any like rigorous comparison, but as I said, for that we need to figure out the rules of the system and see if we then can actually start to compare the two. But I think maybe this is a way forward for like droplet research. And this might be very naive to think that, but maybe it's a new way or different, maybe people already do that, to like simulate these droplet systems, which traditionally is being done with like reaction diffusion system or like reaction diffusion models. And that's, as I said, costly. So if we can treat them like cell automata, like figure out the rules and kind of maybe make a kind of droplet sandbox. I guess, I mean, there's still already stuff that's similar out there, but yeah, I'm basically, I don't really understand cell automata good enough, but that's why I come here and I present the stuff. So I'm always happy to hear from people like all the crazy ideas, because I think crazy ideas are very good. So yeah, just a bit of future work. As I said, we definitely need to improve the quantification, this kind of detection. Maybe we can include some, let's say, like neural networks or like different, let's say, big data approaches like ChatGPT or something like that, or other things like that. Then go to the simulation. Probably we should still do an analytical simulation so we can compare it if we manage to do the other thing. But yeah, so, and then we can use that to explore the similarity. And then once we've done that, then I can increase the complexity, actually, for example, adding the dice so that we get, again, different clusters. So, and maybe we can have many dice. So changing it gives you new rules. So yeah, that's, here's some people involved. Some of them are in the title already, but there's also some people we work with in Italy who are also helping with quantifying the system at the Department of Physics in Trento. And also, for example, Ayumu Ueda, Shinpei's student, and then my current boss, because he gave me a job, which is good, and that job can pay for me to come here. So that deserves thanks as well. So that's it from me. So thank you.